So can you all see the slide now?
Yes, ma'am.
Okay, thank you so
Yes,
much.
ma'am.
Okay, okay. So Huygens principles was something that this Dutch physicist called Christian Huygens, he gave on a theoretical basis. Okay, he tried to explain the propagation of light using a geometrical construction of wavefronts, consisting of wavefronts. Now remember, at this time, the wave nature of light was not widely known. It was not widely accepted, the wave nature of light. Okay, so when Christian Huygens gave these principles, they did not have any value precisely for the fact that there was no experimental evidence to back up these the theory given by Huygens. All right. So, however, although this was the time, this is late 17th century, and it was during late 17th century when I had already told you during our discussion on history of evolution of the nature of light that there was this person called Grimaldi who had observed diffraction, but he had only observed diffraction and he could not he did not really use any theory to explain what he had observed. All right. So this was fairly, areas which were fairly unexplored. So Huygens theories were there, not really explored, although he himself had used his theory to explain reflection, refraction, etc. But even then, the, just because Newton's corpuscular theory had also explained reflection, refraction, etc. So both of them were there, and there was no concrete summon as to which was the correct one. And since Newton was Newton, therefore his explanation was more widely accepted. It was later on that when Thomas Young, and we'll talk about Thomas Young when we do Young's double slit experiment in great detail, so when we start interference, when he used Huygens principles to explain his observation of interference and mathematically used Huygens principles to actually give a formula which could explain totally the results seen in interference. It was only then that Huygens principles got widely accepted and the wave nature of light was finally accepted. So Huygens principles consists of three basic points. And please, if you are asked to write down Huygens principles in an exam, then you have to give all these 3 points. Please don't go to Google and type Huygens principles, because they do not give you these 3 points in the order that they should be. They probably give you everything in one 2 or 3 lines in a single paragraph, and that is not what we want. So there are 3 distinct steps of Huygens principles, because as I told you in the beginning that this is an explanation of propagation of light by geometrical construction. So this construction, just as you do geometrical, you have done geometrical construction in your mathematics classes, geometry, you had done bisection, you have done construction of angles, you have done trisection of lines, construction of quadrilaterals, etc. So they involve certain steps. Similarly, this geometrical construction also involves certain steps, and those are the steps that are to be followed. So the first step is this. This is the first point of Huygens principles, is that every point on a propagating wavefront serves as a source of secondary wavelets. Okay, now let's see what this says. Suppose this blue line here is a wavefront. This is the primary wave. Okay, we have a source somewhere and waves are propagating. So we isolate one such wave front. And so if it's a wave front and we are imagining a point source so that the wave fronts are spherical and we are taking an arc out of one such sphere. Now we can imagine this wave front to be consisting of several points. We can always imagine several points on a certain line, on a certain curve. Okay, so these are the several points on the wavefront. Now what Huygens said is that each such point serves as a source of what? Of secondary wavelets. So you can imagine that small waves, which he has called wavelets. Wavelets means baby waves, small waves. Okay, so wavelets are emerging from these points on the primary wavefront. This is the first point. Okay, what is the second point? These secondary wavelets travel with the same velocity and frequency as the primary wave. So when you draw these secondary wavelets, will you draw all of them to be the same? Will you draw all of them to be different from each other? What will be the direction of propagation? What will be the velocity of propagation, etc.? So this was also given by Huygens, that the secondary wavelets travel with the same velocity and frequency as the primary wave. Clear? This is the third point. Here, this is where my pointer is. The new wave front at any later instant of time is the envelope of the wavelets in the forward direction. So, if I had drawn an envelope of these wavelets here, that would form my actual wave front at a later time. Okay, at that instant of time. So here you see again, this picture is taken from a book. So this is the primary wave front. Each point A, B, C, D, E, etc. they act as positions of secondary wavelets, sources of secondary wavelets. So if you want to find out the wave front at a point of time where the secondary wave is, they have reached a certain position, because all the waves are traveling with the same velocity, so they will reach a certain position at the same time. So suppose you want to find out the position of the secondary wavelets after time t. So you know the velocity of the primary wave. So you draw the secondary wavelets up to time t, and then you draw a an envelope to these secondary wavelets. All of you know how to draw an envelope to a number of curves. So that envelope will be the actual position of the wavefront at that point of time. Similarly, for a plane wave, this is the initial wavefront. Okay, so the points A, B, C, D, E on this initial primary wavefront act as sources of secondary wavelets. Now here the rays are parallel to each other, so these are the secondary wavelets. So with velocity v, they are traveling forward. So you just need to know the time after which you want the position of the actual wavefront. So you draw the secondary wavelets up to that time, propagating with velocity v, and then you draw the envelope to the secondary wavelets at that point of time, and that envelope will give you the position of the wavefront at that particular point of time. Okay, so using this geometrical construction, imagining that every point on the primary wavefront acts as a source of secondary wavelets which travel with the same velocity and frequency as the primary wave, and then drawing the envelope to the secondary waves at a time when you want the actual position of the wavefront, find out of the only light is no wave the wavefront at any point of time can be constructed if you know the initial position and nature coming out. Huygens principle. We the phenomenon. Here you see these are parallel rays traveling with velocity v1 in the rarer medium, and they are traveling with velocity v2 in the denser medium. And we know that refraction means there is a deviation of the ray of light from the actual path. So this is these red lines give me the incident wave front, and these blue lines here give me the refracted wave front. Okay, so this angle I is the angle of incidence, and this angle R is the angle of refraction. I hope I don't need to explain how we get this as angle I and this as angle R. You know enough geometry to know, see that. So if you consider triangles ABC, right angle triangle ABC, and we know that wavefronts are perpendicular to the rays. So this is a right angle triangle, and ACD is a right angle triangle. So if you consider these two triangles, then you can see that the ratio of sine I by sine R is BC by AC and divided by AD by AC. Okay. So basically it is BC by AD. Now in the rarer medium, the light is traveling with a velocity V1. Sorry. So in time t, it will travel a distance V1t. See the point B over here, when it reaches the interface at the point C, in time t, it has traveled a distance v1t. But in that time, when this wavefront reaches C, this wavefront has already reached D, but with a different velocity v2. Okay, so this value BC is v1t, and this value AD is v2t. So the ratio BC by AD is V1T by V2T. In other words, it is the ratio V1 by V2, which is mu, which is a constant. Where mu is it's not reflective, it will be refractive. Someone's audio is unmuted. Can you please mute your audio? So, if you want to say something, please say so. Otherwise, please mute your audio. I am in the presentation mode, so I cannot see whose audio is unmute.
ম্যাডাম আপনি যে মিউট করতে পারেন তো করে দিন, আমার ফোনটা একটু হ্যাং করে গেছে, অসুবিধা হচ্ছে ওই জন্য।
আমি দেখতেও পাচ্ছি না, মিউট করে দিয়েছে মনে হয়। Okay, so the ratio is the ratio of the two velocities, which we know is refractive index. Okay, so refractive index is the velocity of light in vacuum to the velocity of light in the other medium, which means that Snell's law of refraction is proved using Huygens principle. Also, since the incident wavefront, the refracted wavefront, and the normal, they are all lying on the plane of the paper, or not paper here, my laptop screen, your mobile screen, or laptop screen, or computer screen, whatever. So they are lying on the same plane. So laws of refraction are proved using Huygens constructions. Just by wavefront propagation and velocity concept, you can prove Snell's laws and the fact that they all lie on the same plane. In the same manner, you can prove laws of reflection using Huygens constructions. I am not explaining this whole thing because the entire thing is given step by step. So you please follow the steps and see. I am not explaining this.
Ma'am, you're inaudible.